Have you ever wondered what our sun looked like when it was a particularly vibrant, young star? Thanks to the James Webb Space Telescope, JWST, we are now able to see our sun in an entirely new light. This remarkable observation provides fascinating insights into the early stages of stars and the massive processes that may have shaped the early phases of our sun's life. Could we have unlocked another one of the universe's great mysteries with this groundbreaking technology? The JWST stands as a prime example of how cutting-edge technology has revolutionized our understanding of the cosmos. Since its launch, the exploration of the universe has progressed rapidly, with a telescope showcasing its extraordinary capabilities in revealing the deep secrets of space. One of its latest feats involved imaging HH21, an object of incredible brightness. HH21, also known as a Herbig-Haro object, is an exceptionally young star that is already powerful enough to send out strong jets into space, creating a dynamic environment around it. Observations of this object have provided an influx of invaluable data about the early stages of star formation and, by extension, the early phases of our own sun's development. Herbig-Haro objects, first identified in the 1950s by astronomers George Herbig and Guillermo Haro, are some of the most stunning phenomena found in regions of intense stellar development. These objects consist of narrow jets of gas ejected from newly formed stars, speeding into surrounding interstellar space at high velocities. When these jets collide with surrounding gas and dust, dramatic emissions are produced. Before the advent of the JWST, these high-energy jets were already a subject of great intrigue, offering a glimpse into the chaotic processes occurring in stellar nurseries. Stars in their youth are far from gentle. While they may be beautiful, they are also incredibly powerful. The forces driving star formation are immense, and even millions of years into their lives, these stars remain dynamic and volatile. It takes eons for a star to settle into the steady, calm brightness that we associate with our sun today. The Herbig-Haro object HH21, which is located in a star-forming region of the Perseus constellation about 1,000 light-years away, is one of the youngest and closest examples of such phenomena, making it an ideal subject for studying the processes that occurred in our own sun's early years. JWST's observations of HH21 have provided unprecedented clarity, offering detailed views of the intense interactions and processes that may have shaped our sun. In particular, the images reveal two brilliant jets emanating from the center of the object. These jets are rich in molecules such as carbon monoxide and silicon monoxide, offering clear evidence of high-energy processes within the young star and its surrounding environment. One of the most surprising discoveries was the detection of molecular hydrogen within the jets, providing a fresh perspective on the chemical composition and thermodynamic conditions in the early stages of stellar evolution. Furthermore, the observations hint at the possibility of a binary star system forming at the heart of HH21, with the jets likely originating from two stars in the process of merging. The images also suggest that the surrounding accretion disk, which could eventually give rise to planets and moons, may be impacted by the intense radiation from the jets, making it more difficult for stable bodies to form. Interestingly, the jets from HH21 are slower than those from other Herbig-Haro objects, which may indicate that this star is still in an early phase of development or that the processes within this system are less violent than in other stellar nurseries. The ability to observe these key cosmic processes up close and with such high precision marks a major leap forward in the field of cosmology. It paves the way for even more groundbreaking discoveries in the future. The birth of new stars offers valuable insights into how ionized gases and plasma interact with the blazing jets, creating shock fronts that act as visual boundaries for young star systems. These early star surges are similar to the protective heliosphere around our sun, which shields our solar system from harmful radiation. Equipped with state-of-the-art instruments such as the Near-Infrared Camera (NIR-CAM), the Near-Infrared Spectrograph (NIR-SPEC), the Mid-Infrared Instrument (MIRI), and the Fine Guidance Sensor (FGS), the JWST can detect even the faintest light from distant youthful objects that would otherwise be invisible to our eyes. By utilizing infrared technology, astronomers can peer through thick dust clouds and uncover previously hidden corners of the universe. This allows them to gain direct insights into the formation of stars and planetary systems, which are often obscured by dense layers of interstellar dust. Thanks to JWST's exceptional sensitivity and precision, astronomers and space enthusiasts alike can experience a level of detail in cosmic observations that has never been seen before. The telescope not only captures these faint light signals but also analyzes them, providing detailed information about the gas's development and temperatures, as well as the chemical composition and molecular interactions at play. In star-forming regions like Orion, Herbig-Haro objects are common, offering a window into the dynamic and often turbulent environments where stars like our Sun are born. The data from JWST offers an unprecedented look at the forces and processes that give rise to stars, and in turn, provides us with vital clues about the early life of our very own star. The Perseus cluster or similar regions are crucial for studying the chemical processes in space. These areas are abundant in gas and dust, creating the perfect environment for star formation. Stars form from the accumulation of these various materials, which are influenced by the powerful jets or outflows emitted by young stars. These jets, which can travel through space at hundreds of kilometers per second, are just one part of the dynamic processes that occur during stellar evolution. When these jets interact with the surrounding medium, they heat it up, creating the iconic bright arcs and clusters visible through telescopes. Within this visible spectacle, immense physical forces are at work, along with light displays, electrical and magnetic interactions. Interesting observations reveal how these jets interact with the surrounding material, helping to shape the cloud from which the star is born. Each wavelength and color provides valuable data to astronomers, offering insights into these processes. Observing these cycles in real time, especially in their early stages, is akin to directly witnessing the blueprint of a star's development. By understanding how matter is incorporated into the larger cosmic cycle and determining the mass of a star, as well as which elements and gases are involved, we can make significant deductions about the forces at play. This also aids in understanding broader processes related to the development of matter in the universe. Although star formation is one of the most powerful energy processes known to humanity, it's difficult to grasp that a young star could generate winds extending hundreds of light-years into space. Jets from Herbig-Haro objects may be the direct remnants of the immense energy that causes dust clouds to begin rotating and coalescing at the center. It's also possible that these young stars use jets to expel unnecessary energy while simultaneously driving developmental processes in the gas and dust cloud from which star systems are formed. To date, we've observed jets in young, forming stars, but we are also aware of very old galaxies in the universe that produce powerful jets from their centers. Some of these massive jets extend far beyond their galaxies, dispersing vast amounts of material, which ultimately impacts the star's mass and the environmental conditions in the area where stars are forming. The material and energy ejected by these jets can lead to further star formation or other cosmic events. It's also important to consider the role of magnetic fields around young stars. These fields are essential in controlling the accretion process, in which the star pulls in gas and dust from the surrounding environment. Magnetic fields also influence the direction of the jets. They are not only vital in the immediate surroundings of young stars but are present throughout the universe. These invisible forces guide the paths of charged particles and influence the structure and evolution of entire star systems. In our own solar system, the magnetic fields generated by the Sun play a crucial role in maintaining the heliosphere, the protective bubble that shields the entire solar system from harmful cosmic rays. The Sun itself produces a complex and variable magnetic field that governs the arrangement of our planetary system, affects planetary climates, and controls space weather phenomena like sunspots, solar flares, and coronal mass ejections. These solar events can sometimes significantly impact satellite operations and communication systems on Earth, and they also create auroras. Studying magnetic fields in young star systems, such as the HH21 region, is an exciting area of research that is still in its early stages. By understanding how stars evolve in distant regions, we can also gain insight into the history of our own Sun. Our Sun, which is 4.5 billion years old, has undergone numerous changes since its formation in a gas and dust storm. The origins of our Sun help determine how planets, from gas giants like Jupiter to rocky planets like Earth, were formed, as well as smaller bodies like Mercury and Pluto. These bodies were either present in the early stages of the solar system or were shaped by the conditions at the time, contributing to the current structure of our planetary system. The study of the universe through advanced telescopes, such as the James Webb Space Telescope, JWST, opens up new windows into the farthest reaches of space, revealing phenomena that were previously invisible or poorly understood. The JWST represents a leap forward in our ability to explore and comprehend the cosmos. One of the most fascinating aspects of JWST observations is its capacity to investigate regions where stars are in their infancy. These stellar nurseries, scattered across galaxies, are vast laboratories where the process of star formation unfolds. Understanding this process is vital because stars are not just celestial objects. They are the fundamental building blocks of galaxies and the sources of the elements that make up planets and, ultimately, life itself. JWST's instruments, such as the Near-Infrared Camera (NIRCam) and the Near-Infrared Spectrograph (NIRSpec), are specifically designed to detect faint infrared signals emitted by young stars and their surroundings. Infrared radiation is especially useful for studying these regions because it can penetrate the dense clouds of dust and gas that obscure star-forming areas, revealing the hidden processes within. One key feature observed by the JWST is the accumulation of material onto young stars. As a young star forms, it gravitationally attracts surrounding gas and dust, creating a rotating disk known as an accretion disk. This disk is a crucial stage in stellar development, as it provides the raw material from which planets eventually form. The JWST's ability to study the composition and dynamics of these disks offers insights into how planetary systems, like our own, may have looked billions of years ago. In addition to studying individual stars and their accretion disks, the JWST also examines the broader environment of star-forming regions. These regions are rich in subatomic gases like hydrogen, carbon monoxide, and water vapor, which serve as the fuel for star formation. By mapping the distribution and abundance of these molecules, astronomers can piece together the complex processes governing the birth of stars and the formation of planetary systems. JWST observations have also provided new insights into the role of magnetic fields in star formation. Magnetic fields play a crucial role in shaping the dynamics of accretion disks and regulating the flow of material from young stars. Understanding how these magnetic fields interact with the surrounding environment is essential for developing a comprehensive model of stellar evolution. Perhaps one of the most awe-inspiring phenomena observed by the JWST is the outflow of material from young stars in the form of jets. These jets, which can extend thousands of light-years into space, are driven by intense magnetic fields and gravitational forces near the star's poles. Studying these jets allows astronomers to probe the inner workings of young stars and understand how they release energy and momentum into their surroundings.